And thank you everyone for joining this talk. The title is Target Direction Funding and Localization with Phaseless Measurements. Okay. Here is the outline. First is motivation for magnitude only or phaseless measurements. So why are we doing this? Okay. And then is associated ambiguities for direction rival estimation due to less information available, because we are only measuring the magnitude of the signal, not the phase part. And then we propose a group sparsity-based phase retrieval algorithm for direction funding based on this magnitude only measurements. And then we further extend this to target localization. So how do we do target localization based on distributed array networks by employing magnitude only measurements? And then finally conclusions. Okay. First, so motivation. So we know targeted direction funding and localization. So it's an important problem in radar detection and estimation based on antenna arrays. So normally, we have a full measurement, including both the phase and the magnitude of the received signals, right? Many classic direction rival estimation algorithms are based on this assumption. So you have a full measurement of the received signals, like music or ESPRIT. They are well-known, so classic algorithms. However, this would need prior calibration of the whole array system to remove any possible phase errors present in the measurements, so which may not be realistic in many practical scenarios. And phase errors, they are not avoidable as a result. So now, I want to talk about the motivation. So basically, in this context, we will show that, okay, this phase error issue can be avoided by making this phaseless or magnitude only measurements. Okay, to show this, we consider this uncensored uniform linear array. So you see this is a uniform linear array. The adjacent sensor spacing is D, and we have an instant signal coming from this direction theta, and theta is measured from the broadside. So for this model, so we have this data. So XP, this is a standard. So we have this XP is the received signal vector. We have n sensors, so this vector is n by 1. Okay, and then SP is the source vector. Suppose we have k signals coming, then SP, it will be k, a big K by 1. Okay, and then this A theta is a steering matrix. So, and it consists of big K steering vectors. So each steering vector corresponding to one source. And this is a general form for this uniform linear array, the steering vector AK. And then if you have P snapshots, so big P of them, okay, this here, equation 1 is just for one snapshot. And if you have P snapshots, you put them together, put this XP, X1, X2, and so on, put them together into a big matrix. So you have this equation 3. So this X is a data matrix, received data matrix, and A theta again is a steering matrix, S is a source matrix. Here is certainly, I forgot to mention, is noise free. So we are just, we ignore noise for the time being. Okay, there's no noise. And then suppose there's some unknown phase error EN at sensor N of the array. So then you have this new model. So you basically have an extra matrix E. This E is diagonal, and its diagonal elements is given by E to J times EN. So this is a phase error term applied to the received sensor signals. So A times S is the original ideal case, the received signal. So you have this diagonal matrix multiplied with this A times S. And this error term, this error part could be corrected by some array calibration techniques, okay, to some degree, okay. However, it can be eliminated without calibration by simply taking the absolute value of each received signal. So if you take the absolute value, so element wise, so takes absolute value of the received data X, this big X, so you got this data matrix Y. So it takes absolute value, you see, okay, you can apply this to the inside, move it to the inside and separate them. And then this E, because it's a unit, because here it's just a phase error, right? The magnitude is 1. So you take the absolute value, is just 1, 1, 1, is identity matrix. So then here you have this AS, the absolute value, okay? So you can see here, you can't see so after taking this absolute value, you can't see the error part anymore, right? So the phase error has been removed by magnitude only measurements, okay? So that's one way to obtain this magnitude only measurements. In practice, okay, we could directly design a system which only measures signal magnitude. So we don't need to have the full measurement first and then apply this absolute value operation. We can design a sensor which just measure the magnitude of the received signal. So one example is this Rydberg quantum sensor, which only measures the intensity of an impinging electric field. So that's one example for this kind of magnitude only measurement sensor, okay? Now, consider this noise now. So we put noise, you see this is the magnitude only measurement in the ideal case. So we add this extra N, this noise matrix to it. So we have this complete model in this equation 6. Certainly, you may think, okay, for a full measurement system, you should put N inside this, right? AS plus N and then takes absolute value, right? That's one case. So if you have a traditional full measurement system, then you take absolute value, you should put N inside. But if you design a sensor which only measures the magnitude of the signal, and then you have measurement noise, and so in this case, N will be outside of this absolute value, right? And the proposed, so the algorithms, the methods we propose later in this talk, they will apply to both cases. So it can work for both cases, either so N can be inside or can be outside. But the advantage of putting this N to the outside is you can calculate the CRB very easily, right? But if you put N inside, then it's difficult to find the CRB, right? So the main reason is for convenience of calculating this CRB, and the proposed solutions will work for both cases. Now, given this model, a big question is, so can we still perform effective DOA estimation? Okay, so if you check this model, actually, this is a classic phase retrieval problem where only squared signal magnitude is available. So you only have the intensity. So the only difference between here, this model, and the phase retrieval model there is in traditional phase retrieval applications, so such as optical imaging, like denoising applications. So there's usually only one snapshot because you only have one picture, right? This is the one snapshot. So while in this model, so multiple snapshots are available because you can keep making measurements, right? And then, so given this model, so the group sparsity could be incorporated into existing phase retrieval algorithms to solve the problem, to find the direction, okay? However, so due to loss of phase information, there are inherent ambiguities for DOA estimations. If you do DOA estimation directly, you'll find, okay, there's some issues there, okay? So for these associated ambiguities, okay, so first, if there's only one impinging signal to the array, then each sensor will have this measurement of the same signal. So they have the same magnitude, right? So in this case, there's no way to determine its direction, as the magnitude of array measurement with a single impinging signal will stay the same for all N sensors, no matter which direction the signal comes from. So in that case, there's no way you can solve the problem. So you need to avoid the case that there's only one signal. Okay, how can you avoid that case? So to remove this ambiguity, we can simply put one arbitrary source. So you deliberately put one source there. So put one arbitrary source to a direction of convenient choice. So it's up to you. You make a decision about where you want to put this extra source to make sure there will be at least 2 signals present. And the good thing is, okay, certainly you think it's not convenient, right, to always to put some extra source there, but we do not need to know exactly which direction this additional source comes from. So you can put it up any directions. You don't need to calibrate that source. Okay, that's some disadvantage. So just put them anywhere you like, as long as you can make sure there are at least 2 signals coming. So that's one ambiguity. So when you have just one signal coming, but it's difficult to have a further, more general discussion about ambiguities, okay, associated with this magnitude-only measurement, as they are normally array structure dependent. So next, so I will use the URA as an example to show these ambiguities. And for the URA, uniform linear array, there are 3 ambiguities. So one is this mirroring ambiguity. The other one is a spatial shift ambiguity. And then the third one is a spatial order ambiguity. Okay. First is this mirroring ambiguity. This ambiguity refers to a mirrored version of the signal. So the mirrored version means, okay, you take the conjugate of the source signals. So take a conjugate, so S1 conjugate, S2 conjugate, and so on. You have big K of them, right? And then you change their direction to minus theta K. So then basically in this case, this new set of signals coming from this new set of angles, they will lead to the same magnitude measurements as the original ones. Okay, to show this, you can see here, okay, you have this xn, you put this conjugate to this measurement xn, so they have the same magnitude, right? And then you put the conjugate here, so conjugate, and then you can move this conjugate to the inside. And then this conjugate means, okay, you get, because minus j, it will be plus j, right? Or you get this minus here, because sine theta, right? Sine theta k, you can change this theta k to minus theta k. You see here, this one means what? You have a new set of signals, which is so sk conjugate, but the directions is from minus theta k, right? So this set of this new scenario, okay, will give you the same magnitude only measurement, okay? So this Sn will be equal to this case. That means you have ambiguity, okay? So basically, due to this sine theta term, so this mirroring ambiguity will arise for any linear array structure. So as long as you are linear array, then you will have this ambiguity. Now the second ambiguity is called spatial shift ambiguity. It means, okay, a spatially shifted version of the original source from angle theta k by some amount would still have the same magnitude measurements as the original one. Okay, to show this, we consider this, okay, this measurement, magnitude only measurement xn. So you add this extra phase shift. So this extra phase shift is independent of the sources, right? It's e to minus j n phi, okay? And then you can, from here, you can obtain this one, right? You take this n out because there's an n, right? Take the n out. And then suppose this sine theta k plus phi over alpha, this part is still smaller than 1, the absolute value, okay? Then you can find a theta k double dots, a new angle, okay? Give you the same value as this. And then in this case, you see you have a new set of angles, but it gave you the same magnitude only measurement. Okay, so that's this spatial shift ambiguity. And this spatial shift ambiguity, okay, it will not affect the DOA order. So suppose you have sine theta 1 smaller than sine theta 2 and so on, and smaller than the sine theta big K, so big K of them, right, in total. Then after this shift, you still have this relationship, okay? So there's the order of the new set of angles, okay, there's no change. However, there's another ambiguity. We call it spatial order ambiguity. As this ambiguity will change the spatial order of the impinging signals. So that is, okay, if you have the original order, state 1, state 2, and so on, so descending order according to their sign values, then after this shift, we will not have the same order anymore, okay? And this ambiguity occurs when applying half wavelength spaced URA to the full angle range, minus 90 degrees to 90 degrees, and cannot be solved by placing known reference signals. So because if you put known reference signal in those direction, then you can avoid the spatial shift ambiguity. You can also avoid the mirroring ambiguity. But for this order change, right, ambiguity, you cannot avoid that putting any reference signal there. However, we can prove it can be avoided by limiting the adjacent sensor spacing to lambda/4. So if the spacing is lambda/4, then there's no order ambiguity, okay? And the analysis for this ambiguity is complicated and just omitted here, okay? If you want to know more about this, you can find more information from this reference 4. So I will show you the references at the very end of this presentation. Now, how can you avoid these ambiguities? As I said, so one solution is putting more references. Okay, if you put some reference signals there, then you know the directions, then you can use them as a reference and to find the shift and find the mirroring and so on, so to avoid them. But that's not convenient because you could have end up with a large number of reference signals. Okay. And so another solution to this, okay, to avoid this ambiguity issue is, okay, we can employ some specific array structures. Okay, like this one. So we can have this dual array structure like this one. It consists of 2 URAs. The first array is in the horizontal direction, while the second one has a known angle is a displacement. So a theta check to the first array. There's a difference, right? Rotation. And due to this non-zero rotation angle, so any shift or mirroring will lead to inconsistency in the 2 sets of estimated DOA results. So because there's an angle here, so the mirroring and shift for one array, will be different for the other array. And then only the true locations, the true directions, they are common to both arrays, right? So to check the inconsistency of the estimated DOA results, then you can find the true directions of arrival of the signals. So that's one solution, using this dual array structure to avoid those ambiguities. Another one is, okay, just examples. I think there are other structures available. So you can use this uniform circular array, for example, uniform circular array. And this UCA can be considered as multiple pairs of dual arrays, right? Because you have this array, right? Each array, subarray, you have 2 sensors. So it's multiple pairs of dual arrays, right? So they can avoid those ambiguities, okay? And to show that this UCA, okay, to show that, we just examine it in a little bit more detail. So you see, that's the stream vector for this UCA. And for mirroring, signals arriving from minus theta k, generate measurements with the same magnitude from the original ones, right? That's what we mean by this mirroring ambiguity, right? Then you see, okay, if this is original measurement, original sources, original angle theta k, then if you put conjugate here and change this theta k to minus theta k, right? That's a mirror, right? And then you check this, and it's given by this. And this one, normally in general, this one will not be the same as this one, right? So this one and this one, they are normally they're different. So there's no mirroring ambiguity for this UCA. For spatial shift, so you can see, okay, you add this extra phase shift there, and then from here you can, okay, it's equivalent to this. It's an equivalent angle theta nk check. So although this xn check would share the same magnitude as xn at the nth sensor, but this extra angle, right? Extra angle for the corresponding kth signal at the different sensors are different due to nonlinear property of this cosine function and the involvement of this gamma n. So this one is different for different sensors and for different K, right? So this implies that there's no common shift variable phi n to simultaneously keep the same magnitude as xn and the same shifted angles theta and k check for all n sensors. Okay. So UCA, uniform circular array, can avoid this mirroring and the spatial shift ambiguity. But there's another ambiguity actually for UCA. It's different ambiguity. Okay. You can consider the whole range because UCA is uniform circular array. You want to look at basically you are interested in the whole 360 degrees, right? The whole range. So for the whole range from minus pi to pi, the big K incident signals. So if you put this conjugate here, okay, generate a new set of sources, and also add pi or subtract pi from this original theta K, then you see what you find. Okay, you change it to conjugate and add pi or minus pi to the original angle. So you see this one actually is just a conjugate of the original one. So that means what? You have ambiguity, right? So the original signal from theta K or the conjugate version of the original signal from theta K plus pi or minus pi, right? So that's ambiguity. To avoid this ambiguity, we can limit the area of interest to this minus 90 degrees to 90 degrees. Since for this range, so if you add pi or minus pi, then it will exceed the limit. Okay. So actually, so this ambiguity happens to all two-dimensional arrays, considering the full 360 degrees range. The U array would suffer from the same ambiguity, but it's ignored because for U array, the interested angle range is from minus pi to pi, from minus pi over 2 to pi over 2 already, right? You're already limiting it to this range. So you don't consider that ambiguity. So that's the ambiguities issue and how to avoid them. Okay. Now it's group sparsity-based phase retrieval for direction finding. Basically, we want to propose a new algorithm to find the direction of the impinging signals. Okay, based on this magnitude-only measurement. Now we have this model, right, with noise and absolute value of A times S, and this is the magnitude-only measurement big Y, this matrix. And to develop this algorithm, okay, first is a sparsity-based. So we first uniformly divide the whole angle range of interest into G, which is much larger than this N grid points. So represented by angles of theta G, G is from 1 to until this big G. So G could be very large, like 1,000. And the whole range, you know, from minus 90 degrees to 90 degrees, you split the whole range into like 1,000 points, right? Each point, you have a potential source direction, and you have a potential source signal there. And for each direction, you can have a stream vector, and then you put all these stream vectors together, you have this big stream matrix A tilde. So if you split, if G is 1,000, then this one, you know, you have 1,000 columns, basically this A tilde. And similar, this S is a source matrix. And for each direction, each potential direction, you have a potential source. So this source matrix is also very large, right? Suppose you have a big K of them and G is 1,000, then its S tilde will be 1,000 by big K, right? And because you only have big K of them, right? Signals present. So most of the row vectors of this big S tilde, they are zero value because there's no signal there, right? So this big S tilde is very sparse. It's very sparse. If you have 10 signals coming and you G is 1,000, then 10 out of these 1,000 rows of this are non-zero valued. But all the remaining row vectors, they are zero valued. So this is very sparse. And then you can use sparsity based method to solve the problem. So we use sparse representation. So the non-coherent DOA estimation problem can be formulated as a group sparse phase retrieval problem. So here, so basically we want to find this sparse big S tilde also minimize the reconstruction error. This reconstruction error. Y is a magnitude only measurement. This is the received signal, right? Given this S, you get the measurement, and you want to minimize this error. Okay. And at the same time, this L21 norm, you minimize L21 norm. This one basically enforce this group sparsity. So L21 norm means, okay, you calculate the L2 norm of each row of this big S tilde. Then you put this L2 norms into a vector, and then you calculate the L1 norm of this new vector. So in this way, you can enforce group sparsity. Okay, basically you are after the optimization, you will only have a few rows of this S tilde. They are non-zero valued. All other rows will be zero valued. Okay, but this, here gamma is a trade-off factor. Okay, but this one is not convex, right? So you cannot use convex optimization toolbox to solve the problem directly, right? But basically, we just extend the phase retrieval algorithms to the group sparsity to multiple snapshot case. Okay, so we apply this prime technique column by column, and then we can transform this. This non-convex problem can be measurized by a surrogate convex function as this. So here Q is iteration, is index, and this is not difficult. It's a standard process to solve this kind of problems. So basically, it's an update, iterative update. So S I Q plus 1. So given this Q solution, then you can update to this Q plus 1, right? So this is a standard process, and then you can also use Nesterov acceleration to increase the convergence speed. Okay, and then you have this toy bar problem. So the proposed algorithm we refer to as fast group sparsity based phase retrieval. So we call it toy bar. It's published in its IEEE AESS, but later we found quite some typos there. Okay, so here is this is algorithm summary. Hopefully there's no typo in this summary here. Okay, this is the correct version. Okay, and if you're interested, you can check the paper there. Okay, for detail. I will not go through the detail here. Okay, in this talk. Now some simulation results. So performance of the proposed toy bar algorithm is compared with the modified G-SPAR, because modified G-SPAR was used to solve the same problem. Basically, we want to compare the proposed toy bar with this algorithm. We are using this dual array structure, and for the modified G-SPAR, 64,000 iterations are used. So for toy bar, the iterations are fixed at 400. So 400 iterations and 50 random initializations are used to find the global minimum. And the steps at mu is given by this. And the angle between the two subarrays, because the dual array, right, is 20 degrees. Step size of 0.5 degrees is used for initial DOA estimation. And after obtaining the initial DOA estimates theta hat, a new grid with step size 0.05 degrees is formed around this original estimate, including 1.5 degrees to each side. So basically grid refinement, right? And when applying the refining step to G-SPAR, the number of iterations is halved as the number of grid points decreased. And here are some results. So SNR is 15 dB. So we have 3 signals coming from these 3 directions, minus 30 degrees, minus 10 degrees, and 50 degrees. It's relative to the first array because we have 2 arrays there, right? It's dual array. And the number of snapshots is 20, and number of sensors is 20 for each array. And so here, so just want to note that okay, G-SPAR requires prior knowledge of the number of instant signals, while the proposed toy bar does not. Okay, here's some just an example result. So result by toy bar and result by this modified G-SPAR. So both are working, although in this particular case, G-SPAR has a little bit larger error here. You can see, okay. So this red lines, dashed lines, they are the true locations, and the blue ones, the peaks, they are the estimated ones. So there's more errors here than here, okay. And then if you draw the curve RMSE curve, root mean square error of the estimation, and with respect to the SNR, then you see, okay, basically after refinement, so both G-SPA and toy bar, these two curves are working very well, right? They're very close to each other. So in terms of performance for this particular situation, there's not much difference, although this toy bar is a little bit better, okay? Then you look at a particular case, okay, you fix SNR to 15 dB, and then you change the number of snapshots, right? You see the toy bar is getting much better. So this is toy bar refined, and this is G-SPA refined, right? This one is much better than this. So basically, toy bar is more effective, okay? If you look at the running time, okay, look at the running time. The advantage of toy bar is more, obvious, okay? You see the different number of snapshots, 20 snapshots, 60 or 100. So toy bar, so it takes toy bar 57 seconds to find the result for 20 snapshots, but for G-SPA it's 2000 seconds, so much longer, right? So you see all the value, all the cases. So basically, the main advantage of toy bar is fast convergence. So very fast. You don't need to it will not take such a long time to get the result. Okay, give you a result very quickly. So that's the direction finding case. Now we want to extend this work to the target localization case. So for target localization, so source target localization based on network of distributed sensor arrays is a very important problem in array signal processing, right? Here's a model. So we have a source K. Here's a coordinates. You have several arrays here. So here array 1, array 2, and so on. And then they have their coordinates, right? So for this model, for each array, you can have the same model, right? Magnitude only measurements. So you have this D is an array index. So D, you have big D arrays there. So for each array D, the diff array, then you have this data vector ZD. You have this steering vector for this steering matrix for this matrix D, source signal vector for this matrix D, and the noise vector. So here is one note is, okay, this source vector, source signal vector, actually is array dependent. That means what? It's the most general cases. Basically, for each array, you receive different signals. We assume in general, the source signal corresponding to different arrays, they are different. For example, if you have a different time delay, right? So the source signal will be different. And they could be working on different frequencies, right? Frequencies. So this is the most general case. Certainly they can be, they can be independent of D. That means all the sources, all the arrays receive the same set of source signals. That's a special case. But here we just deal with the most general one. And then, so we also use UCA, uniform circular array. So each array is a uniform circular array, and that's the steering vector. And then from the source location, so coordinates, you can find the source direction rival for each relative to each array, right? So say dk. So for the k source relative to the d array, so you can find the direction theta based on the coordinates of the source signal and the array coordinates. Okay, so that's the state dk, the relationship between state dk and the coordinates. And then for the multiple snapshots, so you have big P snapshots, then you put them into matrix form. So same as the single array case we just studied earlier. Now, how to do target localization? So we could apply the earlier proposed direction finding method directly to find all the DOAs relative to each array, and then obtain target locations by finding intersections of those estimated DOAs, right? That's straightforward solution. However, there are disadvantages with this solution. So firstly, since information at the different observers is processed separately to obtain the individual DOAs, it's sensitive to estimation accuracy at each array. And one single unreliable estimate can cause large errors in the location result. So if one array is not working, you get a big error, DOA error, SME error there, then it will, make a big mess of this final result, And so that's the first disadvantage. The second one is, okay, there are also possible pairing and ambiguity problems associated with such a two-step approach. You need to pair them if you have multiple sources there, okay? So that's the disadvantages. Now we want to propose a one-step direct solution to overcome those disadvantages. Okay, so the more effective approach is to jointly exploit information across all sensor arrays by enforcing a common spatial sparsity, as all target signals originate from the same set of target locations. So to do that, so we divide the admissible area of interest into GX and GY, so big GX, big GY grid points along the X-axis and the Y-axis separately, and the GX times GY is big G. So basically you have in total big G potential locations, okay? And then the over complete steering matrix of the deep sensor array can be expressed like this, right? Because for each location, you can find the direction, right? And you can find the steering vector. You put all these steering vectors together, you can form the steering matrix for the deep array, okay? For this big G set of potential locations. And so this is state DG, it's an angle between the G grid point location and the deep sensor array. So you can use this simple relationship to calculate them, okay? Now, for each array, you can have this sparse representation. Right? So ZD, that's the received data matrix for the deep array, and this is the over complete steering matrix. This is the over complete source signal matrix, right? And note that incident sources from an arbitrary grid point would share the same spatial spot in SD tilde, in this ST tilde, and AD tilde, okay? Although the arriving angles with respect to different arrays are different. So what it means is, okay, if for a particular grid point, there's no source signal present, then the corresponding row of this SD tilde will be zero valued. And it will be zero valued for all SD tilde, D from 1 to until this big D. So it's all, so they have the same position, because if you have a zero value row in here, in this SD, then all other SDs, they will have the same zero valued row, okay? And if you have a source present there, then it will not be zero valued. Then all the corresponding rows of this SD tilde, they are non-zero valued, right? So that's they share the same spatial spot. Now we define this new steering matrix covering all these sensor arrays. So A1 tilde, A2 tilde, and so on. So in total, big D of them is a block diagonal matrix. So it's a block diagonal operation. And then you put all the ZD, the received signal matrix for each array together to form a much bigger data matrix. And similarly, for the source signals, you have the source matrix. And you also put the noise together, okay, to form this big noise matrix. And then together, you put all the data together, you have this simple representation. So Z equal to A tilde times S tilde and absolute value and plus this N, okay? So this is similar to the single array formulation, right? So we can, so the source localization problem can be formulated as a joint group sparsity-based optimization problem. So we reconstruct this Z, through sparse S tilde, right? So we minimize this L2 norm of this S hat matrix. So this S hat matrix basically put S1 tilde, S2 tilde, and so on, put them together into this big matrix. So basically, if one row, so if a particular location, as I mentioned, a particular grid point location, there's no source present there, then the whole row, corresponding row of this matrix as big height, it will be zero valued. Okay, so it's a sparse matrix basically, and then you just minimize this error to a norm to enforce group sparsity. And this problem can be solved by this earlier proposed group sparsity-based phase retrieval algorithm Toy bar. Certainly, there's a little bit of difference here, okay, but it's straightforward. You need to modify this Toy bar a little bit, okay, but basically the same algorithm. And similarly, we can employ grid refinement to reduce complexity of the group sparsity-based solution, or we can develop an off-grid solution by employing Taylor series expansion. So you can use this. So we don't do grid refinement. We just use the this Taylor series expansion to approximate that grid, that error. Okay, and there's an algorithm proposed there. So you see in reference 14. And some simulation results. So performance of the on-grid, grid refinement, and off-grid solutions is compared with the existing full measurement on-grid method. So basically, full measurement means, okay, you have both the phase and the magnitude of the signal. Okay, so there are 4 distributed arrays. These are their coordinates, and we have off-grid locations for 2 sources. That's their locations, their coordinates, and the number of sensors is 20. For each UCA, and this is radius, and we have 100 snapshots unless otherwise specified, and the area of interest is this. So in the on-grid method and the initial step of the off-grid method, so 2 meters is used as the step size for the grid unless specified otherwise, and for grid refinement, a new grid with step size 0.2 meters is formed around a distance 1 meter to either side of the estimate location from the initial step. And then some results. So this signal noise ratio is 20 dB, and this is resulted by this on-grid method. Certainly because of the source, they are off-grid, so the estimation is not good. And then result by the off-grid method, have a very good result. And then you check the RMSE versus root mean square error versus SNR over 100 trials without phase errors. So you see this line, this one. So this blue line is a CRB, okay, this is the lowest. And you see this one, this is the full measurement. So certainly you have the best result because there's no phase error. And then above that, you got the proposed method. They are giving you a worse estimation result because they are designed for the case with phase errors, but there's no phase error here. But if you put phase error there, you put phase error there at this ED matrix. So ED is an ND by ND diagonal matrix with each entry being a unit complex variable with a random phase term generated independently from the Gaussian distribution with standard deviation sigma, and SNR is 20 dB. You see here. So at the beginning, when the error is very small, this curve is for the coherent measurement, so the full measurement. So it's giving the best result. But if you keep increasing the error, then the full measurement result, this algorithm will not work anymore. It's keep getting worse and worse, right? Well, this proposed only measurement-based solution, they are independent of phase errors because after taking the absolute value, it stays the same, the data, right? Then you have this flight response. It's independent of this phase error. So at some point, when the error increases to some point, then the proposed one already is outperforming the full measurement solution. Okay. And then this is another one, just change the number of, set the SNR to 20 dB and change the number of snapshots. Again, so we have the performance getting better and better when you increase the number of snapshots. Okay. This is CRB and sigma equal to 0. Okay, this is the case without error, and this is the case. So this is the case. So with error, without doesn't really matter. With or without error, it stays the same. But it's non-coherent. So it's based on the magnitude only measurement. You get this curve. But this one, this yellow curve, this one is coherent, but for sigma equal to 0.2, the large error. When you have a large error, the full measurement result becomes much worse, right? From here, change to here. So, well, this proposed one, so magnitude only based solution stays the same for both cases, 0 or 0.2, stays the same. Okay, no change. So it's robust against phase errors. Okay. Now, conclusions. So in this talk, a new class of solutions have been presented for effective target direction finding and localization without relying on the phase information of the received array signals. So leading to robust solutions to the problem based on magnitude-only measurements. So non-coherent direction finding problem was first studied, and the inherent ambiguities for DOE estimation associated with faceless measurements were discussed in detail with the URA as a representative example. And two structures were provided to tackle the ambiguities issue, including a dual array structure and the UCA. The non-coherent DOE estimation problem can be formulated as a group sparse phase retrieval problem and solved by the proximal gradient method after transforming the original non-convex cost function into its convex surrogate, where the prime technique, leading to an algorithm called toy bar. And then the source target localization problem was studied based on distributed sensor array networks with faceless measurements. And the resultant non-coherent source localization problem was formulated into a joint sparse phase retrieval form and can also be solved using existing group sparsity based algorithms such as toy bar. So as target locations are obtained jointly and directly from the received signals, the proposed solution is also robust against the individual measurement errors. It's also possible to develop off-grid solutions for the proposed methods, and for detail, please refer to our recent publication 14, okay? And further extension to the wideband case can be achieved through the convolutional sparse coding framework. You can see that from reference 15 and 16. Here is a list of most relevant references to this talk. Okay, there's I think 16 of them. Okay, so that's all. Thank you very much.